AI moves fast. Here's what matters. This is AI Daily for January 7th, 2026. Despite boasting a 4.68% performance increase on STEM benchmarks, the AI model Logix-STEM in Archive 2601.01562v1, built on a massive 10M scale dataset, still struggles with a logic problem a toddler could solve. But why? Today, murder-suicide case shows OpenAI selectively hides data after no, Microsoft Office didn't just get renamed to Microsoft 365. Plus our deep dive into Logix-STEM, empowering LLM reasoning via failure. Let's go.
Here's your AI Daily News Roundup for January 6th, 2026. All right, folks, let's jump right into today's top AI news, starting with a really concerning story that broke late yesterday. OpenAI is facing serious scrutiny over its data retention policies after the death of a user. This stems from a recent murder-suicide case where investigators are trying to access the deceased user's ChatGPT logs. Now, OpenAI is refusing to comment on where user data goes after death, citing privacy concerns. This is obviously a complex ethical dilemma, but for us as engineers, it raises critical questions about data governance, user consent, and the responsibilities we have when building AI systems that collect so much personal information. How do we build truly ethical AI, and what are the long-term implications of withholding potentially crucial data in sensitive situations? It's something we need to be actively discussing. Moving on. Remember Microsoft Office? Well, despite some online confusion, it's not being renamed to Microsoft 365 Copilot. It appears to be just a marketing hiccup with a lot of speculation flying around. But the fact that so many people thought it was plausible speaks volumes about how deeply integrated AI assistants like Copilot are becoming in our everyday workflows. As developers, we need to be thinking about how to seamlessly integrate AI into existing tools and workflows without disrupting user experience. How can we design AI features that are helpful without being intrusive or confusing? The line between a useful assistant and a clunky add-on is getting thinner, and we need to be mindful of that. In other news, llama.cpp just dropped a new release, B7642. While the release notes may look a bit technical with mentions of AVX512BF16 fixes, the core takeaway for us is the continued optimization and broadening of platform support for Llama, including macOS, Linux, and Windows. The team is actively working to ensure Llama runs efficiently on a diverse range of hardware, from CPUs to GPUs with CUDA and SYCL, and even ARM architectures. This matters to anyone deploying LLMs outside of massive cloud environments. These optimizations directly impact performance and accessibility, meaning we can run powerful models on local devices, opening up a world of possibilities for edge AI and privacy-focused applications. So keep an eye on those release notes, even if they seem dense at first glance. Also making waves today is a new paper on Archive exploring speech LLMs and end-to-end architectures for multilingual conversational ASR. The paper, stemming from the Interspeech 2025 challenge, delves into how to build better speech recognition systems that understand multiple languages, particularly in conversational settings. The interesting angle here is a comparison between a hybrid approach, combining existing speech models with LLMs, and a completely end-to-end model. This is crucial for us because multilingual AI is becoming increasingly important. Figuring out the best architecture, whether it's a hybrid model or a truly end-to-end model, will dictate how we build voice assistants, translation tools, and other applications that need to understand and respond to users in their native languages. Next up, a critical discussion happening online about GitHub's dominance and its potential impact on the open source ecosystem. The argument being made is that GitHub's position as a near monopoly gives it undue influence over the direction of open source. Now, this impacts us as developers because it raises questions about centralization versus decentralization, vendor lock-in, and the long-term health of the open source movement. we need to be aware of the power dynamics at play and consider alternatives or strategies for ensuring open source remains truly open and independent. It might be time to explore platforms beyond GitHub or contribute to the development of decentralized alternatives. And finally, two stories capturing attention on Hacker News. First, a Y Combinator-backed company called Revision Dojo is facing accusations of astroturfing on Reddit. The claims allege that they're using fake accounts to promote their IB test prep materials. This is a really bad look and serves as a reminder that ethical marketing is paramount. For us AI practitioners, it's also a lesson about the potential misuse of AI for generating fake content and manipulating online discourse. We need to be building tools responsibly and actively combating the spread of misinformation. Second, an article titled Google Broke My Heart is sparking a lot of discussion about the changing landscape of the internet. It's a personal reflection on how Google's dominance has reshaped the web, often at the expense of smaller websites and individual creators. While not directly AI related, it underscores the broader impact of large tech companies on the digital world, a landscape in which AI is playing an ever increasing role. That's the news for today. Now, let's dive into our deep dive topic, the ethical considerations of using synthetic data for AI training. I just saw another paper drop on Archive, this one called Logic's STEM, and my first reaction was, oh great, another model that's supposedly a genius at reasoning. We get one of these every week. They all claim to be state-of-the-art on some obscure STEM benchmark, and then they can't solve a basic logic puzzle from my niece's activity book.
I know exactly the feeling. It's like benchmark hypnosis. But I actually dug into this one, and the model itself isn't the most interesting part. It's the how they built it. The final model is almost a side effect of the process, and that process is something a developer can actually learn from and maybe even replicate.
Okay, you have my attention. Don't just tell me it's data algorithm co-design because that sounds like a marketing term. What does that actually mean in practice? What did they do?
Right. It's all about the interplay. So on one hand, you have the data. They built this enormous data set, Logic's STEM SFT, with 10 million examples of long chain of thought reasoning. And it's open source, which is the first big deal for developers. It's one of the largest of its kind.
10 million is a huge number, but I'm immediately skeptical of quality. Is this just scraped and reformatted Stack Exchange posts? Because garbage in, garbage out is the oldest rule in the book. And how is a small team or an individual developer supposed to even handle a dataset that size? I can't load that into memory.
That's the first smart thing they did. They had this really meticulous 5-stage data curation pipeline. It's not just scraping. It's annotation, aggressive e-duplication, and decontamination to make sure benchmark answers aren't leaking in, then distillation from more powerful models, and finally stratified sampling to ensure diversity. They're trying to build a gold standard distribution, as they put it.
Okay, so they cleaned their data. That's good MLOps hygiene, but it's not revolutionary. What about the size problem?
They addressed that directly. They released the full 10M version, but also a downsampled 2.2 million version. That smaller one is specifically for people like us, folks who might be fine-tuning on a single machine with a good GPU. If you're using a framework like Axolotl or Hugging Face's TRL library, you can point it directly at the 2.2 million dataset and get started without needing a massive cluster. They're actively thinking about the developer workflow.
All right, so a good, clean, practically sized open source dataset. That's a solid contribution. I'll give them that. But you said the model was a side effect. That implies there's a more interesting algorithmic piece.
Exactly. This is the part that clicked for me. They call it failure-driven post-training, and it's not as complicated as it sounds. Think of it this way. You do your standard supervised fine-tuning, your SFT, on that big data set. You get a pretty good model, but it's not perfect. It has bugs.
Okay, like any piece of software, it fails on certain test cases. So what?
So, instead of just tweaking the learning rate and trying again, they treat it like a real debugging cycle. They take their trained model and run it against a whole suite of problems. They don't just count the failures, they analyze and cluster them. They find the failure regions, the specific types of reasoning where the model consistently falls apart.
Give me a concrete example. What's a failure region?
Sure. Let's say you're building a model to be a coding assistant. After your first SFT run, you find it's great at Python list comprehensions and basic boilerplate, but it completely chokes on anything involving asynchronous programming or Kubernetes YAML configurations. It just hallucinates invalid syntax. That's your failure region. Async code and K8s configs.
Right. So normally I'd go back and try to find more async examples, more Kubernetes tutorials, and manually add them to my dataset. It's a pain.
This is where their process gets clever. The failure-driven part means they use this analysis to synthesize new data. They take a powerful generator model, maybe GPT-4 or Claude 3, and prompt it to create hundreds or thousands of new, high-quality examples specifically targeting those weak spots. They generate complex async I/O problems with detailed step-by-step chain-of-thought explanations. They generate tricky Kubernetes stateful set configurations with annotations explaining why each line is there.
So it's not just adding more data, it's adding highly targeted bug fix data. Almost like writing a unit test for a failing function, but instead of code, you're writing a targeted piece of data to patch the model's understanding.
Precisely. Then they take this new synthesized targeted data and do a second round of SFT, or even use it for reinforcement learning. It's like a targeted patch for the model's knowledge gaps. The result is that the model improves dramatically where it was weakest without having to retrain from scratch or find a dataset 10 times bigger.
Okay, that actually is a different way of thinking. It's an iterative refinement loop. It's SFT, then test, then generate patches, then SFT again. So from a developer's perspective, how do I implement this? Is there a failure-driven SFT library I can pip install?
Not yet, but you can see how you'd build the pipeline. This is more of a recipe than a ready-made tool. You'd have your fine-tuning script, maybe using PyTorch FSDP. After it runs, you'd have a CI step, like a GitHub action, that triggers an evaluation script. That script runs your new model checkpoint against a holdout set of complex problems.
And that script would need to do more than just report accuracy. It would need to log the failures and maybe even use another model, like an embedding model, to cluster them and find patterns. 20% of failures are related to calculating torque.
Exactly. Once you have those failure clusters, the next step in your pipeline could be a script that calls the OpenAI or Anthropic API. It would use the failure analysis to generate prompts like create 100 novel physics problems about torque and rotational inertia, with detailed, correct chain of thought solutions suitable for fine-tuning a large language model.
And the output of that gets dumped into a new directory, which becomes the input for the second stage of fine-tuning. You're basically building an MLOps pipeline for self-correction. You could containerize each step, a Docker container for SFT, one for evaluation and clustering, one for data synthesis, and then kick off the second SFT job.
Now you're thinking like they are. It's a closed loop, and it's much more efficient. Think of the trade-offs. You could spend 6 months trying to manually curate the perfect data set, or you could spend 1 month creating a good enough data set and then build this automated refinement loop that patches the holes much faster. It's the difference between waterfall and agile development, but for model training.
And that's why they saw such a big performance jump. They mentioned a 4.68% average improvement over the next best 8B model. That's a significant leap in a field of diminishing returns. It's not just from the data, but from this targeted patching process.
That's their core claim. It's the co-design. The data curation engine produces a great foundation, and the failure-driven algorithm builds the skyscraper on top of it, reinforcing the specific floors that are wobbly.
So let's bring this home. If I'm leading an AI team at, say, a biotech firm, and we're trying to build a model that can reason over complex molecular biology papers, what do I do with this paper tomorrow?
First, you look at their open-source Logix STEM SFT dataset. Even though it's STEM-focused, the reasoning structures in there, the multi-step logic, the causal inference, are probably very similar to what you need. You could use their 2.2 million dataset as a powerful base for your own fine-tuning. You'd add a smaller, high-quality dataset of your own proprietary biology data on top. That's your first SFT run.
Okay, so I get my base model. Then I'd build the loop. I'd create an evaluation set of a few hundred really hard questions from recent research papers that I know the answers to. I'd run my model, and I'd find that it's great at genetics, but consistently misunderstands protein folding pathways.
There's your failure region. So your next step isn't to go find 10,000 more papers on protein folding. It's to use GPT-4 to synthesize 2,000 perfect examples of chain-of-thought reasoning about protein folding, based on the types of errors your model made.
And I'd use that synthesized data for a second, much shorter and cheaper fine-tuning run. The goal is to specifically fix the protein folding knowledge without messing up the genetics knowledge it already has.
Exactly. You're performing targeted surgery on the model's brain. This is a much more capital-efficient way to get to a state-of-the-art specialist model than just trying to brute force it with a giant generic dataset.
What are the failure modes of this approach, though? It sounds great, but what goes wrong? I can imagine the synthetic data could introduce its own subtle biases or factual errors if the generator model isn't perfect.
That's a huge risk. Your synthetic bug fix data has to be extremely high quality. If your generator model has the same blind spots as the model you're training, you're just reinforcing the failure. You need a powerful, often proprietary model for the synthesis step and a very robust validation stage for the generated data. You can't just blindly trust the synthetic output.
So you almost need a human in the loop or another AI to act as a reviewer for the synthetic data before it goes into the second training run, another step in the pipeline.
Yes, absolutely. A validation stage is critical. But even with that overhead, it's likely faster than manual curation. The other potential issue is catastrophic forgetting. Your targeted second SFT run could accidentally damage the model's performance on the stuff it was already good at. You have to be careful with your learning rate and maybe mix in some of the original data in the second pass to remind it of what it already knows.
So if I'm building a RAG system, let's say with LangChain or Llama Index, this logic stem model could be a much better reasoning engine to sit on top of my retrieved documents. Its ability to follow long chains of logic means it can probably synthesize answers from multiple documents more effectively than a generic chat model.
Absolutely. Imagine feeding it retrieved chunks from 3 different technical manuals. A standard model might just summarize each one. A model trained like Logic STEM is more likely to correctly follow a causal chain across all 3 documents to answer a complex troubleshooting question. Its reasoning is just more robust.
And the fact they open sourced both the 8B and a 32B parameter model means you can make a trade-off. For an edge device or a lower latency application, you grab the 8B model. If you need maximum reasoning power in your data center, you deploy the 32B version. Having that choice is huge for system architects.
Right. It's a very practical, engineering-focused release. They're not just publishing a paper, they're publishing a toolkit, 2 models, 2 datasets, and a methodology.
So the real takeaway for me isn't just Logic STEM is a new smart model. It's that we should stop thinking of fine-tuning as a single monolithic step. It's a continuous, iterative process of debugging and patching our models with targeted synthetic data.
That's the insight. It's treating model development like software development. You don't just compile once and ship. You have builds, tests, bug reports, patches, and release candidates. This paper provides a clear blueprint for what that Agile workflow looks like for building state-of-the-art reasoning models. It's a shift in mindset.
That's AI Daily for today. If you found this valuable, take a second to subscribe wherever you get your podcasts. And if you're on YouTube, hit that like button. It really helps us reach more people in the AI community. For deeper dives and weekly roundups, sign up for our newsletter at aidaily.beehive.com. Share this with a colleague who needs to keep up. See you tomorrow.